Thank you. So the subject of this presentation it's actually an important issue, is how to control the color to allow for more pozzolan to be used in cement. So first, I'd like to give a quick overview of our company. These are the fields where the company currently provides services and equipment. We go from anything from grinding to calcination to alternative fuels, and even on the quarry side into the calciners and CFD. So we are well spread and can serve the industry in different topics. We are well spread around the world. We have been established about 40 years ago. We have 7 international offices, more than 1,000 references, 300 in cement only. And we understand ourselves as a trusted partner. Going to the topic of CO2 emissions, this is where we believe we can act and help our customers with on the plant efficiency and clinker quality. So we can definitely help you on improving the quality of clinker and the efficiency of your plant, thus reducing CO2 emissions. On the alternative fuels, we can master different techniques to achieve the goals on reduction of fossil fuels, clinker replacement, and hydrogen as well. And when we're talking about clinker replacement, is the very core of this presentation. So going for a green cement is one of the ways of reducing it is by replacing clinker by supplementary cementitious material. So over the last years, of course, the preference will be to use natural pozzolans, but whenever you don't have it, you might rely on the possibility of synthetic pozzolan made out of thermal processing. And this is the whole palette of different SCMs that can be used. The good thing is that there is clay everywhere in the world. Different types and different aspects. Some of them are tougher to deal with. Some are easier to deal with. But basically, you can find clay deposits all over the world, and it is relatively well spread. So there's a good chance this is a good substitute for cement, for a clinker, as long as you can treat it properly. So our company provides 2 options for thermal activation of clays, one being the flash calcs and the other being the rotary kiln, the rotary calcs. So both technologies, or you can choose from one or the other, depending on your specific requirements, but we can offer both technologies. Now going to the color issue, we know that most of the cases, when you start calcining clay, what you first see is the color shift towards red or pink. And this can be a problem, not exactly a real problem in terms of the physical characteristics or development of the strengths or anything like that. It's just a psychological influence on the buyer's decision. Some buyers, I would say most of them, are really concerned about presenting to the market a certain palette of color and try to avoid the red. So what is behind that is how to deal with this. If most of the clay after burning becomes hematite, it will become reddish. If you can get it to a high temperature and keep it in the magnetite form, then you might be possible to have a different color, tends to gray or black. But in most of the case, but just burning in the traditional way in the clay, you get a red or pinkish form of it, and this is not very welcome. So I would regard this the color issue as one of the main issues which prevent people from moving faster towards replacing clinker with calcined clay. So this is one example of clay that you can see it's very red, and it promised to be very, very red after we calcine that. But turns out we can deliver this as an option. So there's different ways of doing this, getting some raw red clay into nice gray calcined clay. And the topic of this presentation is actually to explain how FCT delivers an alternative solution to accomplish this grayness. So looking at the color control methods available, one of them is just keeping the kiln in the reducing conditions. So the rationale here is to reduce the oxygen availability, to try and convert to magnetite and to keep magnetite as such, which tends to be darker and less red. You try to keep the back-end oxygen low by physically controlling the kiln, but also injecting fuel in the feed or even in the kiln discharge. So by adding fuel, you can have a localized reducing condition, and you can probably get a color, a dark color, avoiding the pink or the red. The good thing or the pros of doing this is relatively low capex, but the cons is depending on where you inject the fuel, you might have an increased heat consumption and VOC and CO emissions. And treating those emissions can be very, very expensive. Although the capex for injecting is low, but the capex for controlling emissions can be fairly high. So this is the traditional way. An alternative way is quenching. So we try to freeze the conversion of magnetite. The hematite becomes magnetite. Magnetite is kept in its form as long as you freeze the material down to keep this phase still existing. You can water spray at the kiln discharge. You can have an indirect cooling. It could be regarded as low capex, but I leave a question mark here depending on what you have to employ to get to this indirect cooling, for instance. And you're going to have increased electrical and heat consumption. So those are the traditional ways of controlling color in calcined clay. And this would be the so-called the FCT way. We have a patent for inorganic modifiers. So what are inorganic modifiers? Basically, what we're trying to do once we have iron in the clay, we try to capture it and convert it in other species. So the actions is to determine the best reactant to combine with FeO3O4 or Fe2O3 and to kidnap this form of ion. Well, the advantages is typically it is followed by an improvement in the concrete properties of the calcined clay or LC3 cement. And the cons we can definitely discuss about it, but it's a case by case. So what's the rationale behind this? Let's go back into the clinker technology. When we are starting to heat up the feed material, we are losing CO2, while the clay faces are intact, pretty much intact here, till it gets to a point where it starts to be converted in something else. So the clay forms start to form aluminum, ferrites, and along with calcium. So these new forms that we have here on being formed out of clay are the ones we are being studying now. So what we see is that iron tends to, and also aluminum, they tend to react preferably with calcium. So there's something about using calcium to kidnap iron. So iron, calcium, aluminum compounds are formed, and the iron oxide is consumed. So here's the key point here. We want to get rid of the red color coming from the iron. So we should try and get as much as possible this conversion or consume this iron oxide. So what we see is that once you get to a certain point, that the system calcium iron oxide, they can be achieved in several tests. And we have confirmed this in many different ways, and we see this reaction going on. So as we add calcium to the clay, the iron, it reacts preferably with the iron, forming this and forming this. Turns out that this compound here, the ferrites, they are not red. They tend to be even green or black. So just giving an example, imagine that you have such a red raw clay, and then you start adding a source of calcium to it and submit it to a pilot test. You can see they are mixed together, but they don't have to be interground. So you just co-feed them to a rotary kiln. What you get from this is a product that, by not controlling specifically the atmosphere, nothing like that, you get a gray color. So this test was made in a facility that we have, a pilot plant in Brazil for clay calcination. And so this is the result. What you can see here, and I have to mention that the way we measure color, it's a system of L, A, and B. So just to make it simpler, A color should be as low as close to zero as possible. We try to get to 2.5 A color, so reducing the redness of the material. So we want to measure how does the color A behave. So as you can see here, this one should give you about 10 to 15 a color A. And the results that we get here from the experiment is, starting with a clay of a color A of 12, we can reach easily less than 1 by introducing limestone to the mix and co-feeding it to the kiln. And the LC3 cement becomes fairly low or fairly gray as we want it. So this is just an experiment done in a pilot plant. So one may ask, well, would it work in the real life? So a bit of what is the real life here. As you can see here, we went to extreme situation where we get a very red raw clay, and we want it to become a gray cement as a supplementary material that provides gray color. So what we do is simply add this clay and blend it volumetrically to a source of calcium, which we call the inorganic modifier, that after burning gets to a very gray color. So this one, we don't even have to measure the color A, but as you can see, this is, it resembles a lot gray clinker. So the results were quite promising in the pilot scale. They were validated in the industrial operation. This was a clay producing 1,000 tons a day clinker kiln or pozzolan kiln. And as you can see here, it's very satisfactory to see the result in terms of color. So not only that, the same trial in the industrial scale with 15% iron oxide, when you compare the concrete made out of pozzolan cement without inorganic modifiers and with inorganic modifiers. So both are pozzolanic cement. The only difference that here we have added limestone to the feed of the calcined clay kiln. And what we saw is that the loss, this is a relative loss in reactivity compared to the OPC. 1 day strength without the inorganic modifier was 94%, while with the inorganic modifier, we could get to the same result as an OPC for 1 day. For 3 days, we are better off with this. With 7 days, we still kept higher, and then it flattened out in the 28 days. What the message behind this is that we managed, by the utilization of an organic modifier, to obtain better results in early strengths, which is one of the alleged weaknesses of this the whole utilization of calcined clay for cement. So we can overcome part of the loss in the reactivity of LC3 compared to the OPC cement. The other thing that we saw is that the blend that you achieve is lower, which means the clay becomes a bit coarser when you add inorganic modifiers compared to the clay calcined without inorganic modifiers. By being coarser, the cement gets coarser and the water demand reduces. And this is very, very important. Actually, this is key for the performance of concrete. Whenever we're moving from ordinary cement to LC3, what we see is an increase in the demand of water. And by using organic modifiers, you reduce this water demand. So It somehow helps you in the not only in the mortar but also in the concrete. So yes, we're talking about adding limestone or any calcium-bearing material to the feed of a kiln. And okay, we will increase the heat consumption by doing that, and we will increase the CO2 emissions. But any method, and it's easy to say that, any method of color control will increase both operational costs and CO2, meaning you have an increase in heat consumption, have an increase in CO2 emissions by using any method of color control. Can be water. You can imagine when you add water to a kiln, you're going to increase the heat consumption, and as a consequence, the CO2 emission. The fuel in the feed also you're going to increase because not all the energy is being used by the kiln, and then you're just wasting some fuel by adding it to the feed. And not to mention the VOC treatment, because you're putting fuels in the inlet, and then you have VOC emissions in the exhaust gas. All this will increase your heat consumption. All of this will increase CO2 emission. But still, if you want to do this, I would like to compare the methods. And the calculation that we've done for a case study is that if you consider that you are using pet coke in the feed of a kiln to control color, or coal, or if you're using modifiers, which is our proposition here, or if you use water, or if you use pet coke, but you still have to get rid of the VOC, these are the figures. You're going to have an increase of CO2 by controlling color with pet coke or coal, but a slightly better or less increase in the heat consumption or the emission increase, and water will a lot, and then you have RTO as the one that takes a lot of energy to get rid of the color. So in the same trend goes for the heat consumption. The heat consumption, the one with the lower increase in heat consumption, it's proven to be the inorganic modifiers. So in the end, although you're using calcium carbonate as a means to control color, and you are emitting CO2 out of the calcium carbonate, the overall heat consumption and the CO2 emission increase is less than the other methods. So that's one important feature of this inorganic modifier solution. So what are the steps when you're doing the research and the development of industrial scale trial? First, you have a thorough analysis of the raw material and the chemistry. You look at the composition and the mineralogy of the raw materials to see which one fits better for your specific application. You investigate the suitable inorganic modifier sources in terms of quality, cost, and effectiveness. The plant process assessment, you go for a whole assessment of the plant to see the possibilities where to inject the inorganic modifier, how to do this. We do bench scale, we do pilot scale testing recommended even before the industrial trial. And then you run the industrial trial and get the analysis of the industrial tests, the mortar and concrete testing, and finally you go for SO3 optimization and concrete optimization. So we believe that we can provide you with this option to control color, which is a main issue in the industry, but we have to assess in a case-by-case analysis. It's just not one solution fits all. So as a conclusion, I'll wrap up my presentation with there are several solutions for calcined clay. So we're ready to support you in selecting the most appropriate method and deliver the best solution. Inorganic modifier is a proven method for color control, and it also can compensate for the low aerial strength development overall. So I think this is a good contribution for the future endeavors in calcined clay business, where you can control color and in a very affordable way with less emission increase and still get an enhancement in the concrete properties. With this, I finish my presentation and thank you for your time and interest.
Thank you very much, Pedro. Fascinating new solution to the conundrum of color in calcined clay cements, and it's a valuable contribution to the topic. So thank you for presenting that. Good research and really interesting behaviors that you observed. I mean, it was interesting that you can actually improve early strength, lower the water consumption through these inorganic modifiers, which is as you mentioned, a significant problem for calcined clay cements. I was wondering if you saw a difference in your testing between rotary and flash calciners in when you're using the color control. I know that they have different capabilities, characteristics, if you like, in terms of color control. What were your thoughts on that?
Excellent question. Well, to get the combination between calcium and iron, you need to form a very incipient liquid phase, which means you cannot do in the flash calciner. This is specific for rotary kilns.
Right.
There are different methods that we apply for reducing gases and so on for flash calciners, but this specific one is for rotary kilns.
Okay, very good. There was a question. Did you observe any effects in terms of emissions when using inorganic modifiers?
Sorry, can you repeat that one,
In
please?
terms, did you observe any effects in terms of the emissions, the SO2, that kind of thing?
You should burn the material in a slightly higher temperature that you would do with the calcined clay. So you might be affected somehow in the NOx emissions. And pretty much this, as SOx are different, they're going to be released either way. But and the CO2 will increase in comparison to not using it. But as I mentioned, in all the options for color control, you have an increase in CO2.
And can I just ask about the inorganic modifier itself? Is that it's a limestone, is it? Is it just that the chemistry of the limestone has to be matched to the raw material? Is that the...
Yeah, it's not that something that we sell. We sell the technology or actually the support for running tests, but we get to the site and find the right limestone or any calcium source for it. So it depends on the chemistry of it, but it's something that our clients have in their site for sure.
Okay. And is it always possible? Or are there cases where you can't find the raw material?
I think it's always possible. You can also purchase limestone, if you will. You can purchase lime, if you will, and if you don't have any around you, if you're just a standalone operation for calcined clay. But typically, if this operation is close to the cement plant, there's plenty of calcium there.
Okay. And what levels of iron content is it applicable to? Does it work within a range, or are there limits?
Well, typically you start needing it at 5% iron oxide because it starts getting pink, and then you need to do something about it. So from 5 up, we've tested up to 26% with very successful results. Of course, as the more you have to, the higher the iron, the more you have to add inorganic modifier to compensate because it's a reaction between calcium and iron.
And just a more general question, one that it's always kind of troubled me in terms of the product itself. I mean, can the market accept red colored cement in any situations? I mean, for example, if you're building internal infrastructure that will be concealed, is there actually a market also for calcined clays that haven't been color controlled?
Or there is, yeah, as you mentioned, infrastructure is one of them, but in the general use of cement, so which is the most massive quantities for general utilization in construction. I just saw one country in the world accepting it dearly, the utilization of pink cement. So it's very rare to be very well accepted, pink cement being very well accepted.
as a mainstream product.
Absolutely.
Yeah, in bagged cement, especially in the developing markets where bagged cement is the primary or the dominant mode of sale. Very good. Well, that's a fascinating presentation. Thank you very much for sharing that new technology, new information here on Cemtech's webinar. So you've wrapped up the year for us, Pedro. Thank you very much. And
Thank you.
thanks to